All right, so chapter 38 and 39, they are all about quantum physics. So chapter 38, we're going to talk about photons and how we should treat uh, no, we should treat light as a particles, and also we're going to discuss matter waves. We're going to discuss Schrodinger's equation. So quantum mechanics is different from classical physics because quantum mechanics deal with the atomic level, microscopic, and so that's what's the difference between quantum mechanics and Newtonian mechanics. So when we talk about when we talk about light in previous chapters, you learn that we should we treat light as wave because it possesses the wave property. For example, it can interfere, it can be diffracted, and there's also polarization. So all this points to the fact that we should treat light as waves. But in the early in 1900 or 1905, during that time, there were experiments that seems to indicate that you cannot treat light as wave because that does not explain some of the experimental results. So in 1905, Einstein proposed that we should treat light as a particle, which we call photons. Okay, and he further proposed that light has duality. It means that sometimes it behaves like a wave and sometimes it behaves like a particle. Okay, so this chapter is basically the beginning of the quantum mechanics. Talk about some of the important things. In the beginning during the beginning of quantum mechanics era. So duality, as I mentioned, light can behave like waves or particles. So from the wave perspective, we know that when you have a wave that's propagating along in space, there's a wave speed, there's a wavelength, there's a frequency that quantify the wave, and the frequency and wave and velocity are related by this. For any wave, it will have this property. And we know that when light behaves like a wave, it will also have this kind of property. So in other words, frequency is equal to speed of light over the wavelength. For other waves, then of course that c will be replaced by v, the velocity of the wave. Okay, so this tells you that it is when light behave like a wave, it will have this property. Now, on the other hand, when we treat light as a particle, as a photon, then each photon will carry energy, carry energy, and that energy is proportional to wave frequency. So we can see it's a very neat connection between the wave property and the particle property, because the frequency they both have the frequency in this perspective. So you have the energy of the photon is equal to a constant, Planck constant, in terms of frequency. So the Planck constant comes with two different units. So it really depends on which one is easier to use, more convenient to use. So you will have the 6.63 times 10 to the negative 34 joules times second, or 4.14 times 10 to the negative 15 electron volt times the second. Okay, so in addition to the photon has the energy. So now the energy of light comes as a packet, and each particle, we call that photon, has this energy and momentum. So it also comes with the momentum, and the momentum for photon is basically calculated using energy over the speed of light. So energy is hf. So you have the hf and then over c. So that's hf over c, and that's equal to h over lambda, because when you utilize this expression, so we know that the momentum of the photon is equal to h over lambda, or e over c, and e is h times f. Okay, So also I want to mention that when we talk about duality, this is like when you have a coin, it comes with the two faces. So they coexist. But sometimes we when you flip the coin, you only see one side. And so this is equivalent to when we design an experiment and only one side of the coin is showing up. Okay, but it doesn't mean that the other side does not exist. It's just that the way you toss the coin or the way you design your experiment, only one side will be revealed. Okay, so put in that context when we think about duality. Okay, so next thing is that I mentioned that there are some experimental experiments that have the result that cannot be explained by classical physics. So this is one example, and this is the photoelectric experiment. So the design of the experiment is that we have this the target material, and we have this what we call the collector, and then it is connected to a voltmeter and the ammeter. So we're going to we can measure the voltage difference. We can also measure the currents flowing in the circuit. And here's the battery, and here's the adjustable resistor. So what this experiment was about is that we can shine a light on the target, and so in classical view, when we treat light as a wave, if we shine a very bright light, which means that high intensity meaning that it has high amplitude of the oscillation. Remember, electromagnetic wave consists of electric field and the magnetic field. So when the light is bright, meaning that the amplitude of the wave is large. So classically, if we shine a high intensity light on the target, the electron that is the electrons that are bound on the bound on by the target will be released because it received energy from the incident of light. So you would expect that electron will be released from the target, and it's going to it's going to flow to the collector, or it's going to have a current which we call a photoelectron. The photoelectron is going to flow in the circuit, and we can adjust the battery until and reverse the direction, so until that all the most energetic particle let me see. So the most energetic electrons are turned back before reaching the collector. Okay, so basically that's how the experiment was designed. So the expected result was that the higher the intensity, the more energetic that of the electron, and because electrons are more energetic, that requires a higher potential to turn it back. However, the experimental result, actually showed differently. It actually showed that when the intensity of light is below certain frequency, it does not register any it does not register any current, meaning that there's no electron ejected from the target. And regardless how bright the light that you use, as long as the frequency is below certain frequency, that photoelectric effect does not occur. And when we increase the frequency, even the dimmest light can actually produce the photoelectric effect. So that puzzled the scientists then, because it contradicts what what the way property of light. So then how do we explain the experimental results? Okay, so before we move on to the next slide, I just want to say that the voltage that will turn back the most energetic electrons are called the stopping potential, and of course the kinetic energy of the electrons is associated with the stopping potential, because the amount of energy that would turn the electron back will be the electric charge times the stopping potential magnitude. Okay. And so the experimental result says show that this quantity, the maximum kinetic energy, does not depend on intensity of light source for a given frequency. Okay, and so so then this is actually the experimental results. So after you change the frequency, and then you found that the stopping potential, which is the kinetic energy over the electric charge. If you recall, we have that K max is equal to E stopping potential, right? Okay, and so this is after you've done the experiment, you measure the stopping potential as a function frequency. We found that the stopping potential is actually a function frequency, and the for the electric effect will not occur when the frequency is below a certain frequency, and it depends on the material. For, let's say, for copper, there's a color frequency that might be different from the when you are using, let's say, iron. A different material, it will have a different color frequency. But regardless, they all behave like this. That is the potential, the stopping potential is a function of frequency. Below certain frequency, for the electric effect does not occur. So then, how do we explain this experimental results? It looks like that the energy of the electron is proportional to the frequency, and that frequency is the frequency of light. So Einstein then proposed that if we abandon treating light as a wave, and instead we treat light as a particle, and each particle, each photon carries an energy that is, if you remember, we call that HF. If the energy of the photon is HF, and then each target, when the electron, let's say this is the target, and you have the electron that's bound to in the target, and that's because because of electric force. So if you're given enough energy, then the electron will have the chance to escape. But then first of all, this energy must overcome the binding energy, between the electron and the nucleus, and that binding energy, which we call our work function. So if the incident photon has an energy that's higher than the work function, then the electron will be able to escape. Okay, and if the energy is actually is larger than the work function, then the electron not only escape but actually acquire a kinetic energy, and that's all based on the conservation of energy. So we can see that when we treat light as a particle, and when the particle has the energy that is proportional to frequency, then that can explain this result, because if the energy of the photon is has a frequency that's lower than the certain minimum, then for the electric effect will not occur, because it does not have sufficient enough energy to break the binding between the electron and the nucleus. Okay, but if the energy of the photon is large enough, then and especially when the higher the frequency, the larger the energy, then you would expect that the kinetic energy of the electron will be much higher, which in turn will make the stopping potential larger. Okay, so based on this experimental result, we can also see that we can easily deduce the Planck constant and also the work function. So how do we do that? Let's look at the next slide. So next slide is based on the conservation energy. So as I mentioned, electron, in order for electron to escape from the target, it has to have enough energy to break the electric force that's binding electron to the nucleus, and that energy, that force will have the electric potential energy, and that is what we call the work function. So you will have and then based on the conservation of energy, so energy of photon is equal to the kinetic energy of the electron, the maximum kinetic energy of the electron, and then plus the other work function. So if we rearrange this, we know that the maximum kinetic energy is equal to EV, right? And then so if you divide E, to every turns, and then rearrange this, then you'll find that the stopping potential is the function of frequency, and this is the vertical. This is the y-intercept. So from the y-intercept, you'll be able to figure out what the work function is, and different material will have a different work function. And then from the slope, you'll be able to deduce what the Planck constant is. And their experimental result shows that their H value is very close to, it is a 6.63, 6.63 times 10 to the negative 34. Okay, so this shows you that by this experiment, it seems that the wave property of light cannot explain the results. But if we use the particle property of light, then we can explain the result very well. Okay. So the next one. So the next one is another experiment that's also equally important in quantum mechanics. It's the Compton's experiment. So this is Compton's experiment. So Compton experiment is that, okay, I have a target. Again, I have a target, and now I'm going to, I'm going to shine an X-ray onto the target. I'm going to have a detector. And that detector can move around, can scan from this side to that side. So it's a function of the angle, phi here, and then they're just going to measure the wavelength and the intensity of X-ray. Okay, so X-ray, it is has a higher energy. So we know that it comes with a shorter wavelength. Just so you know. So you have the X-ray incident on the target, and then you would expect that just have the if you incident a wavelength lambda, then the outgoing wavelength of photon of X-ray should also have the wavelength lambda. Okay, you didn't expect that there's a change in wavelength. However, from the wave property, because when you have light with a wavelength that's incident on the target, then when it's emerging from the target, it should remain the same wavelength. It should not change. However, what they found was that when they scanned through this angle, they found that the cell, there's always like, on the horizontal, that's the angle, and vertical is the intensity. There's always like two wavelength. I'm sorry, horizontal is actually wavelength, and the vertical is the intensity. They found that when they scan, when they scan through moving from this end to that end, they found that the intensity that sometimes shows two peaks. So classically, you would expect just one peak, and that would be the original peak. However, when they did this experiment, they found that they actually registered two peaks. The only one that only showing one peak is when when the angle is 0, which means that your detector is directly in front of it. So and then you measure lambda. But then at any other angle, we found that the peak, I mean, there are actually two peaks, two wavelengths that's showing up, and one of them is the original wavelength, and the other one has a longer wavelength. We know that when you have a longer wavelength, it means that it has a lower energy. So how would you explain this results when the energy, when you have a lambda prime that has a lower lambda prime that is longer, which means that it has a lower energy of wave, and this is X-ray. So the result from the intensity versus wavelength plot shows there's a one peak center about the incident wavelength, and there's another one we call that lambda prime that is longer than lambda. And by this amount, so you can see that you can find the difference between the peak difference. So this difference is what we call delta lambda, and this delta lambda is called the Compton shift. Okay, and how do we calculate delta lambda? So I'm just going to show you the results here. So the Compton shift can be calculated, and by using this equation, which is Planck constant over the mass of the particle. Let's say this, if electron is ejected, which we're going to discuss that later, then this m will be the mass of electron, and c is the speed of light, 1 over cosine and the angle. So the angle is this angle. Okay, so this the quantity in front of a parenthesis is called the Compton wavelength. So this other terminology, you want to make sure that you know which one is which. Compton shift is delta lambda. Compton wavelength is h over mc. And so if you know the original wavelength, if you know the another wavelength, of course you can just find the difference, and that is your delta lambda. So in other words, there are two ways to find delta lambda. One is this one, or the other one is this one. So we can see that how much wavelength lambda prime is really depends on where you detect the where you place your detector, the angle phi here, because this quantity, the Compton wavelength, is a constant. Okay, so then Compton was thinking, how do I explain this experimental result? That doesn't make sense, because you only expect one wavelength, but now you actually showed up like two, and also the wavelength, the other wavelength is changes when the angle changes. So then you heard about Einstein's photoelectric experiment, and you heard about Einstein's proposed explanation that when he treats light as a particle, then it becomes the interaction between the particle and the target. So he was thinking to himself, maybe he could also use that same same thing to explain this. So he tried that. So he was thinking, what about if I treat this as a two particle collision problem? Would that would I explain my results? So this is the electron on in the target, and this is the X-ray. So when incident the X-ray on the target, this has become, if we treat X-ray as a photon, so that becomes a tiny particle with the energy, and that energy is related to lambda, is inversely proportional to lambda, right? Because E is energy is equal to h times f, and that's equal to hc over lambda. Okay, so if you know lambda, then you will know the energy. So this becomes a two particle collision problem in a two-dimensional case. So when you collide the electron, then there's an outgoing photon, and then you have the electron that's being ejected with the kinetic energy, if there's a sufficient enough energy for the electron to acquire. So you can see that this becomes the collision problem. So this is before collision. One is coming to the electron, and after collision, this outgoing is going this way, and this is the electron that's going that way. So based on the conservation of energy, then you would set out like this. So you have the HF, which is the energy of the photon, that's equal to the H prime, which is after collision, which is the energy of the photon after collision, and then plus K. And then in this case, we can not just directly use K by 1/2 mv squared, because the X-ray is highly energetic, and so the electron would actually move at the speed that is actually substantial, and so you cannot just use 1/2 mv squared. Instead, the kinetic energy, you will have to use this form. But if you don't, that's okay if you don't know that, because this is actually a relativity, result from relativity, which is not covered in physics 214. But suffice to say that the kinetic energy of the electron is actually the mass of the electron, and then times this gamma minus 1, and gamma is this quantity, and v here is the velocity of the electron. Okay, and because it's it's pretty high, is actually close to the speed of light, so we have to adopt this expression for kinetic energy. And so when you do this, and then this is two-dimensional, so you set the conservation of linear momentum in the horizontal direction, conservation of linear momentum in the vertical direction, and then you will come then you will get to the and then after you do some substitution and work out the stuff, then you'll find that your delta lambda, which is lambda prime minus lambda, that's just equal to h over mc, and then times 1 minus cosine the angle. Okay, so that's basically, you can see that when you treat X-ray, instead of when you treat X-ray as a photon, that also explains the experimental results. Okay, so this two experiment, the photoelectric experiment and also Compton experiment, that kind of shattered, then the lens scientists that believe that light was away, and then they then people start thinking that maybe we should treat light as a particle, but then Einstein actually he went a step further. So, we should treat light as, that sometimes behave like a wave and sometimes behave like a particle. Okay. All right. So, so then, so then the next thing I want to mention is that, when do we treat light as a particle? When do we treat light as a wave? It really depends on how your experimental design, the observer. And this is like you have when we treat light as a wave. And this is you have a light that's propagating light as a wave, and they produce the interference pattern, and then you see this the fringes and things like that. And for the Compton, so you have the particle. So it's like you have the particle. So this is the source of particle, and this is the detector, and it just goes, and somehow it can go path one, it can go path two, and they might interfere with each other. Interfere. So there's an interference, and then what shows up, so in other words, this we know that you start out with a particle and it ends up as a particle, but then in between, we can treat that as a it travel as a probability wave. Okay, so the duality of light forces us to abandon classical view of light waves. We can think of light as a photons in the source and is absorbed in the form of photon in the detector and travels as a probability wave between source and the detector. So it's kind of philosophical, but this is how we interpret it. When you have when light when light behaves like a wave or behaves like a particle. So so then this actually shows you another example to think of light as a probability, a photon as a probability, it is travel like a probability wave, because the top one shows the typical double slit experiment. So you have the light passing through the single slit and then passing through, so it becomes a wave front, and you have wave propagating through and then passing through two slits, and then they're going to interfere with each other and produce this interference pattern. So this one, is easily, you can recognize that that's interference pattern, and this is the what you will see. But then, so on this one, this is the results from another experiment. So instead of sending a wave, light wave, passing through the slit, how about that sending one photon at a time? So these are the results. When we send photon one at a time, and then we just let it go for some time and see what kind of a pattern it will show up. So we can see that when you have one photon, when you incident one photon at a time, so you go through the first slit, that's no question about that. And then when it comes to the double slit, where does it go? Does it go through the S1 or does it go to the X2? So it has equal probability. And then so you can see that you got random dots on the screen. And then as time goes on, more dots are accumulating on the screen. You still don't see any pattern. It seems that they are randomly distributed. But then after some time, you just keep going, you'll find that it actually produces some sort of interference pattern. It's very similar to this one, right? So it looks like, even though you're sending one photon at a time, but then it actually produces kind of a interference pattern. So photon can, even though it's a particle, it actually produces interference pattern. And so this is like, so this is, as I mentioned, this is the built up, as a function of time. So this is like after several months, you start seeing pattern. So that's very interesting. So you can see that photon is so, it is, it behaves like a wave, but it just on a much larger time scale. Okay. So then, so this kind of behavior, when you treat when light actually has the duality, so then one next question is, would other particles, particles like electrons and protons, do they also behave like that? Why do we ask that question? Because what people did, this is another another experiment that people did, that we have a target, okay, and then they send the X-ray, and then it will produce an interference pattern that we know, so if you remember the Bragg's law, you send the X-ray through the target. Sometimes if that has a regular lattice spacing, then you can produce a diffraction pattern. So we all know that. So X-ray can produce a diffraction pattern. So then people, some scientists actually replace the X-ray with the electrons, and just send a string of electron and an incident on the target. What they found was that when the electron is that go through the target, it also produces a diffraction pattern. So you can see that. So this is the diffraction pattern that is produced by the electron. So is if you remember the kind of a diffraction pattern produced by X-ray, you would easily recognize that the diffraction pattern produced by electron actually is very similar to diffraction pattern produced by the X-ray, except that the bright is like a negative of the diffraction pattern produced by X-ray. So in other words, X-ray will produce a bright fringe in the center, but this one is actually dark, and then you will and the X-ray will produce the dark fringe, and then this is like you see the electron is produced like this, and also you'll see that this is like it seems like it comes with like double layers. So like you have like instead of like just one, you actually have like two, and this is like two. But regardless, you can see that when you send electron through a slit, it also produces a diffraction pattern. That can only point to the fact that electron can behave like a wave, meaning that electron can also has the duality, okay? And because electron has a mass, so we call that matter wave, okay? So what is a matter wave? Matter wave is that moving particles like electrons as a matter wave that carries energy and momentum, just like photons. And photon is massless. The rest mass is zero. But then an electron has the rest mass of the electron is non-zero. Okay, so we call that matter wave. So this particles do display wave-like characteristic. So the wavelength, so we can actually have associate that wave with the wavelength, and that wavelength is given by the h over p. And h is again Planck constant, and p is the linear momentum, okay, mass times velocity. And this wavelength, we call that de Broglie wavelength, okay? So whenever you have a particle like proton, electrons, you can use this equation to calculate the wavelength of the matter wave. And so here's the example showing the so this one showing that electron can behave like a wave, because when you look at this is a computer simulates interference fringe, but then that is instead of using the light, this is used with the electrons, and you can see that it produces the interference pattern. And this and then this picture shows that this is the interference pattern or diffraction pattern produced by X-ray. This is the diffraction pattern produced by electrons. You can see that they are very similar to each other. Okay, so that kind of further demonstrate that electron can be treated as a wave, and that wave is matter wave. So then if that's a matter wave, then there must be, how do we describe the wave behavior of the electron? So in mechanics, for the mechanical waves, we use there's a wave function, and so for matter wave, there's also a wave of the equations that can describe the behavior of the matter wave. And that equation is called the Schrodinger's equation. Now, Schrodinger's is the person that who proposed the thought experiment of the Schrodinger's cat. So if you're interested about that, it has a very philosophical and also has to do with the probability. So you're welcome to Google that, or just look up the stuff in the textbook to find out more about the Schrodinger's cat. But so now we just want to see what is Schrodinger's equation and the wave function. So Schrodinger's equation is this, that that involves the energy of the electron and also the potential energy of the system. And this one, the psi here is the wave function. As you can see, the psi is the solution to this Schrodinger's equation. So psi here is a function of x, y, z and time. So we can actually separate the time dependent part, so that this lowercase psi is the wave function as a function of x, y, z, and this is e to the minus I omega t. Okay, so so this is a solution. So this is a solution of the wave function of the Schrodinger's equation, and so a matter wave, we should consider a matter wave as a probability wave. Okay, and to find the particle at a given position, depending on the probability density. So when you the solution square is the what we call probability density, and usually it's a complex quantity. What does that mean? It's a complex quantity. It means that it has a real term. It also has an imaginary term. And because it has an imaginary term, so it has no physical meaning. In order to find the physical meaning, you have to find the probability density. So the imaginary term will not be there. Okay, so for one dimensional, let's say if we have electron that has the energy E, and if you have a free electron, then which means that there's no force on the electron. If there's no force, then there's no potential energy. So the potential energy here will be 0. Okay, so this term does not contribute when you have a free electron. So you have the Schrodinger's equation that describe how the free electron free electrons behavior, which is the d psi square over dx square plus 8 times pi squared times the mass of the electron over the Planck constant square, and then times the energy of the electron, and then times the wave function that's equal to 0. So you can see that this is a second order differential equation with no source term, or what we call the homogeneous second order differential equation. Okay, so so the energy of the electron, when there's no potential energy, then it can be described by kinetic energy. So that's 1/2 mv squared. So you can see that this equation becomes d psi square over dx square plus this, and then E becomes 1/2 mv square, and then times the wave function equals 0. So the task is to find out the solution of this, the wave function. Okay, so how do we do that? And so we can rearrange this, and knowing that our P is equal to mv. Okay, so P is equal to mv, and we have the mv squared, so we can actually square, on both sides, square, and then you have the m here. So this will be this term, and then so you have the m there. So then you can let's move on to the next page. So then you can express your the quantity here in terms of P. So it becomes 2 pi and then P over h squared. Okay, so if you remember, when we treat electron as a matter wave, and so there's a de Broglie wavelength, and the de Broglie wavelength is is equal to P over h. So so your, let me just write here. So P is equal to h over lambda, right? So when you have the P over h, then that becomes 1 over lambda. So you have the 2 pi over lambda, right? So this just, So when you have the 2 pi over lambda, what is that? That is actually your wave number. K is equal to 2 pi over lambda. So this equation becomes this equation. So very simple. Second order differential equation, and you have the K here. And by now you should have known that when you have a second order differential equation homogeneous, then the solution would just be this. That will be a coefficient times e to the ikx plus b times e to the minus ikx. And the a here is the way that's going in this direction, and the b coefficient is related to the term that is going in the reflection. So the outgoing and the reflective part. Okay, so you can see that this wave function comes with the imaginary part and the real part. So we cannot physically measure that. So in order to do the measurement, what we need to do is that we need to find the probability density. And so this part just we put the time dependent part back. So when you rearrange this becomes e to the ikx minus omega t, and then e to the minus I, and then this one. Okay, and knowing that e to the I theta is equal to this, and this is this, so that just basically exponent it's not. And what I really want to say is that because we're treating this is a case when you have a free electron, and when you have a free electron, we're going to set there's no reflection, so we're going to set b equals to 0, meaning that the solution now does not contain this term. So your wave function would just be this. Okay, so we place a with the let's say psi naught and then eikx. So again, this is the complex numbers. It cannot be detected. So we need to find the wave the probability density. So how do we do that? We would do the psi, absolute value of psi square. And in order to do that, which means that you would do the this multiplied by the complex conjugate of this quantity. So you have this, and then multiplied by the complex conjugates of this quantity, which means that the I becomes negative I. So when you multiply them together, that just give you e to the ikx plus and then times the e to the minus ikx. So you add the arguments in the exponential together, that just give you 1, and e to the 0. So e to the 0 will give you 1. So when you do finding the probability density, that would just be the psi naught square. Okay, so that's how you that's how you do it. And basically this is this is just what we have what I said earlier. So what does that mean? It means that after, when you have a free electron and when there's no force, so the only energy present is kinetic energy, and the electron and then we found that the solution to the Schrodinger's equation is this, and this is a constant, and this is probability wave, and this basically tells you that the probability of finding the electron along the x-axis is is equal regardless what location you're at. For example, let's say this is the x-axis, and you have an electron. So electron could there's an equal probability of finding electron here, finding electron there. There's no preferred location for the electron to be at. That's why probability density is a constant. Okay, and I explained so that because this electron being a free particle, so you would expect that it can just be detected at any point. Okay, so that kind of match the picture when we start out with the other a free electron. Okay, however, when we later we found you'll find that when you have electron that is trapped either in a, let's say, potential well, so there is a potential energy, then the electron is being confined, then there is a specific location for the electron to be in, or prefer location, meaning that at certain locations that you will have a high there's a higher probability of finding the electron. Okay, but for this case, the probability of finding electron at position x1 or position x5 will be the same. Okay, so so that's that. So we can see that we can use Schrodinger's equation. So we set up the Schrodinger's equation, and then you can find out the solution, and that solution can tell you the probability of finding electron at what location. In addition to that, when we use Schrodinger's equation, when we solve for the wave function, the other thing that we're interested is finding the energy of the particle, and that will be the topic of next chapter. Because once you find the energy, once you find the solution, you'll be able to deduce the energy of the particle, and then you'll find that for trapped particles, energy is quantized. So that's what we call the quantum mechanics, because that has to do quantization. All right. All right. So the next thing I want to talk about is Heisenberg's uncertainty principle. So what exactly is Heisenberg's uncertainty principle? So basically, that principle says that both the position and the momentum of a particle cannot be measured with unlimited precision. Okay, so the product of the uncertainty of each quantity is subject to a Heisenberg uncertainty principle. And uncertainty principle is that the uncertainty in position in x position times the uncertainty in the momentum in the x position in the x-axis has to be greater or equal to h bar. And what is h bar? H bar is h over 2 pi. So in other words, you cannot have both position and momentum, with zero uncertainty, because that would defy the uncertainty principle. The product of this has to be greater or equal to the h bar. And likewise, because we're living a three-dimensional, you would expect that the same for x, that will hold for the delta y times delta py, and also delta z times delta pz has to be greater or equal to h bar. Okay, and so take for example for the free the free electron. We know that free electron, it has equal probability of finding electron, meaning that meaning that it can just move freely. Okay, so the uncertainty of the free electron will actually be considered as infinity, because it has equal probability. You don't really know where the electron will be. So in that case, the uncertainty of the electron is infinity. And if the electron, we know that we previously we said that P is equal to mv. So if we know, with this we have the precise, if we know P, then delta P, can be considered to be 0. So so if that's 0, in order to satisfy this equation, this must be infinity. So when you multiply that, that will actually be greater than a non-zero value. Okay, so this is the Heisenberg's uncertainty principle, and so this is that tells you that you cannot have both quantity with knowing the both quantity with unlimited precision. However, it does not specify how delta x in relation to delta py or delta pz and vice versa for this, that. So only this will only hold for the same axis, same direction. Okay. Now the other thing about the Heisenberg's uncertainty principle is that there's another equation that holds as well. And delta E is the energy uncertainty in energy, and delta T is uncertainty in time. So you have the delta E times delta T that is greater or equal to h bar. So what does that equation tell you? That equation tells you that the time, we know that time, if there's an uncertainty in time, then if there's an uncertainty in energy and there's uncertainty in time, so we could actually change the time or go back in time or go forward in time. All right, so there's a delta T there. So it sparks a lot of imaginations, among the scientists, because based on this, it seems that it is possible for time travel, provided that you have enough energy that can break the time domain. Okay, so but that's something that's interesting. So yeah. Anyway, so so the next one, the last the last thing I want to talk about of this chapter is that there's another application of quantum mechanics that we actually experience every day is the barrier tunneling. Okay, when I say we actually experience that every day, it's because the keyboard actually utilize the tunneling effect. You have electron, the current that go through the the circuit, and that actually utilized is applications of the concept of barrier tunneling. So what exactly is barrier tunneling? So let's say you have electron, okay, and when you eject an electron and encounter the barrier, so this is like on the vertical, that's energy. So let's say you have the barrier, meaning that the energy, so this diagram shows that you have an electron that actually has an energy that's lower than the energy of the barrier. Classically, if the energy of electron is less than the energy of the barrier, you will not expect that electron to be found on the right side of the barrier because it just does not have enough energy to overcome that barrier in order to pass through. Let's say you have an electron that has energy of this height, you can just go through that, okay, no question about that. But then if you have an electron that actually has a lower energy than the barrier, then you should know, then it will actually bounce back instead of passing through. However, in quantum mechanics, when we treat electron as a wave, then there's a tiny little probability that for the electron to be found on the other side of the barrier. And this is what we call the barrier tunneling. And this is what the keyboard, when you use the keyboard, and the electron will have the energy that's actually less than the energy that inside, there's a barrier. But then, it can actually, we go through the barrier and be found on the other side of the tunnel. Okay, so so here it just says that the electron with the energy less than the energy of the potential, then it will be reflected from the barrier in classical physics. However, in quantum mechanics, electron is a matter wave, so there's a finite chance for it to tunnel through the barrier and appear on the other side. And this so this shows you the wave function. So the solution wave function, you can see that before, prior to the barrier, it can be treated like a free particle. So there's a wave function that's like sinusoidal form, and then classically, you would just go to zero. Okay, you would not expect the electron to be present inside the barrier or outside or on this side of the barrier. However, with the matter wave concept, we found that there's a non-zero probability for the electron to appear on this side. And so kind of like passing through the barrier, okay? So, and then once you have the electron on the outside, meaning that there's a current, so that's how, the current can still like passing through and do what we ask the electron to do. So anyway, so the transmission, so here quantity, that just for your information. So there's what we call the transmission coefficient. How much of an electron will actually appear on the other side is actually proportional to e to the minus 2k L. L is the thickness of the width of the barrier. And the K here is, you can recognize that it's actually from the Schrodinger's equation. So it's A times pi squared mass of the electron or the particle, and then the barrier's height, and then minus the energy of the electron, and then over h squared. Okay, so you can see that this is described. So it is a tiny value, but it is a non-zero value. Okay. And also, why do we say that classically you will not expect that to come the other side? Because k, because energy is k plus u, right? And if you have the E is less than u, then it must be that k has to be less than 0. But then k has the expression of 1/2 mv squared, which is always positive. You can't expect that k to be negative. So classically, you will rule out that you would not expect electron to appear on this side. But then with quantum mechanics, when you treat that as a wave, then you can just it can be found on this side. Okay, so this is this is like another scenario. Sometimes we I don't know, when you watch the TV or when you watch the movie, and let's say you have the people that can actually passing through the wall. It's kind of similar to that. You have the wall in front of you, and you can just walk some in the movie, of course, you see that people walk through the wall. And so in classically, of course, that would not happen. We don't see that. We don't see that. But then, in quantum, in the quantum world, that you can actually find that the person appear on the other side of the wall. Okay, so it's kind of a similar analogy. Okay, so that concludes this chapter, and there's a lot of packed with a lot of interesting thoughts. And then on chapter 39, we're going to discuss the more realistic case when it deal with the hydrogen and things like that.